Howdy guys, Jimmy Song here. Welcome to another episode of White Paper Wednesday. This is a show every Wednesday I try to do that, reads through some of the technical papers. Given that we're all stuck at home and kind of doing our own thing, I thought it would be a good time to go back to the original paper, the Satoshi White Paper. And this is kindly posted in nakamotoinstitute.org, and you can take a look at it directly on there. I think it's, if you go to the Satoshi Nakamoto Institute, nakamotoinstitute.org, the first link is literally read Satoshi's white paper. So I'm going to read it through for you, and I'll try to tell you what it means, and go through some of the misconceptions especially, and so on. So let's, without further ado, let's get started. Bitcoin, a peer-to-peer electronic cash system, Satoshi Nakamoto, October 31st, 2008. It's kind of crazy, but it's already been almost 12 years since this white paper was written. But it was released on October 31st, 2008 by an anonymous developer, Satoshi Nakamoto. And it does say a peer-to-peer electronic cash system. This is hailed by all of those people on Bitcoin Cash as if it means a very particular thing. You'll see very soon that it does not. All right, so let's start with the abstract. A purely peer-to-peer version of electronic cash would allow online payments to be sent directly from one party to another without going through a financial institution. So even in the first sentence, it should be very clear what Satoshi Nakamoto means by electronic cash. Would allow online payments, so first of all, it's electronic, right? That's what he means by electronic cash, to be sent directly from one party to another. So one party to another. So, usually transactions online happen through a third-party intermediary, but it says without going through a financial institution. And that's the difference between cash and almost any other form of money, is that cash has no third-party intermediary, whereas something like Visa, Amex, Google Pay, Samsung Pay, Octopus Card, M-Pesa, whatever, WeChat, any other form of monetary transfer requires a third party, and that is the thing that's very different in cash than anything else, is that there is no third-party intermediary, and that it says it right there in the first sentence. A purely peer-to-peer version of electronic cash would allow online payments to be sent directly from one party to another without going through a financial institution. So, this is something that Bitcoin Cash people, like, seriously, they only read the title and think they understand it. First sentence pretty much spells out why, Satoshi Nakamoto used the word cash. It's because there's no third party. That's the key thing. Digital signatures provide part of the solution, but the main benefits are lost if a trusted third party is still required to prevent double spending. And this is the big problem, is that signatures, I can sign something and give you something, but you have no idea if it's good or not, right? And that's the main thing, is that you need somebody to be able to verify and not just take my word for it that it's that the money that I'm sending you is good. And this is the big requirement, because up until the time that this white paper was created, a trusted third party was required in order to do that. We propose a solution to the double spending problem using a peer-to-peer network. Okay, so there is a network involved that helps to solve this double spending problem. How do you know that the check that I'm sending you is good or not without a third party or like a bank to tell you that it's good? The network timestamps transactions by hashing them into an ongoing chain of hash-based proof of work, forming a record that cannot be changed without redoing the proof of work. So we'll get into what proof of work means, but it's hash-based proof of work. That's the key sort of thing that unlocks it, besides digital signatures. The longest chain not only serves as proof of the sequence of events witnessed, but proof that it came from the largest pool of CPU power. And this is where mining comes in, and we'll get into that in a bit as well. As long as the majority of CPU power is controlled by nodes that are not cooperating to attack the network, and this is where the whole idea of a 51% attack comes from, they'll generate the longest chain and outpace attackers. The network itself requires minimal structure. Messages are broadcast on a best effort basis, and nodes can leave and rejoin the network at will, accepting the longest proof of work chain as proof of what happened while they were gone. So the key thing about this network is that there's no permission needed to join, and you can leave or join at any time. And because proof of work is something that's objective, you just follow the longest proof of work chain, the one with the most work. But that's what the abstract describes. Now we get into the details. Introduction. Commerce on the internet has come to rely almost exclusively on financial institutions serving as trusted third parties to process electronic payments. While the system works well enough for most transactions, it still suffers from the inherent weaknesses of the trust-based model. Completely non-reversible transactions are not really possible since financial institutions cannot avoid mediating disputes. The cost of mediation increases transaction costs, limiting the minimum practical transaction size and cutting off the possibility for small casual transactions. And there is a broader cost in the loss of ability to make non-reversible payments for non-reversible services. With the possibility of reversal, the need for trust spreads. Merchants must be wary of their customers, hassling them for more information than they would otherwise need. A certain percentage of fraud is accepted as unavoidable. These costs and payment uncertainties can be avoided in person by using physical currency, but no mechanism exists to make payments over a communications channel without a trusted party. All right, so this is the main introduction or the motivation for this whole white paper. Everything on the internet, to some degree, relies on some level of trust. If I'm paying, Amazon for some books or something with Visa, and Amazon and I have a dispute, the credit card company essentially has to adjudicate that dispute, and they can't avoid mediating disputes. And similarly, because of that possibility of mediation or reversal or whatever, there's friction. There's transaction costs every time, and this is very apparent in any sort of credit card. The reason why the merchant takes like 2 or 3% every time is because there's a possibility of reversal, and that could be very costly for either the merchant, the consumer, or the credit card company, depending on like how everything plays out and what guarantees were made by whom. So the whole point of this is the need for trust causes us to lose a lot of privacy, and you can see that merchants must be wary of their customers, hassling them for more information than they would otherwise need. And with that possibility and everything else, non-reversible payments are just not really possible. And especially for services where you're paying for something that someone does for you, if you have the possibility of reversal, it's really kind of like a free option in many ways. So that's the motivation, right? Is that there is a trusted party, right, in commerce on the internet, and we want to remove that trusted party. So how do we do it? What is needed is an electronic payment system based on cryptographic proof instead of trust, allowing any two willing parties to transact directly with each other without the need for a trusted third party. Transactions that are computationally impractical to reverse would protect sellers from fraud, and routine escrow mechanisms could easily be implemented to protect buyers. In this paper, we propose a solution to the double spending problem using a peer-to-peer distributed timestamp server to generate computational proof of the chronological order of transactions. The system is secure as long as honest nodes collectively control more CPU power than any cooperating group of attacker nodes. So it's talking about 51%. But I just want to emphasize here in the introduction, the word cache is used mainly to talk about the lack of a trusted third party, right? The lack of a trusted third party. That is like if you read the abstract, and I just read that and I just read the introduction, the thing that comes up over and over again is the fact that there is no, the whole design of the system is to remove that trusted third party. And if you put that trusted third party back, you're kind of, doing you're subverting the whole design of the system. It doesn't make any sense. So, all of these altcoins that are like, oh, we're faster, whatever, but then centralize it in exchange for all of that. It's taking out the whole point of the first two sections of this white paper. And this is why anybody that knows anything about Bitcoin is like, okay, if you're going to centralize it kind of like, why wouldn't you just use Visa or something? It doesn't make any sense. All right. So 2, transactions. We define an electronic coin as a chain of digital signatures. Each owner transfers the coin to the next by digitally signing a hash of the previous transaction and the public key of the next owner and adding these to the end of the coin. A payee can verify the signatures to verify the chain of ownership. So essentially, this is describing something like a UTXO model. And a UTXO is an unspent transaction output. So every transaction has some signature and a hash that where here are the coins that this owner 1 has. And then they send it to owner 2, whose public key is in there. And basically, the owner's private key can sign and create this transaction in the next one, and so on. So you get paid to your public key, but you sign with your private key. So each time, it's a chain of these signatures, and it's a UTXO model. So every time you're spending, you're giving up control of the amount. The site that I'm reading from is in the show notes. It's nakamotoinstitute.org/Bitcoin. All right. So the problem, of course, is the payee can't verify that one of the owners did not double spend the coin. So I, as a private key owner, I can sign this one, but I can sign lots of other ones. So how do I know which transaction is good? A common solution is to introduce a trusted central authority or mint that checks every transaction for double spending. After each transaction, the coin must be returned to the mint to issue a new coin, and only coins issued directly from the mint are trusted not to be double spent. And this is the bank model, right? This is how banks typically do it. Is they're the trusted party. If you try to cash the check, they will tell you if it's good or not. If it's a bad check, then they won't give you the money. They're the ultimate arbiter. The problem with this solution is that the fate of the entire monetary system depends on the company running the mint, with every transaction having to go through them just like a bank. And this is the big problem with altcoins, is that they have a central foundation or some central entity, usually a founder or something like that runs the whole thing, that decides the policies of the bank or the mint, if you will, and they can change things at any time. So this is the problem that none of the altcoins really solve, where Bitcoin actually does. We need a way for the payee to know that the previous owners did not sign any earlier transactions. For our purposes, the earlier transaction is the one that counts. So we don't care about the later attempts to double spend. The only way to confirm the absence of a transaction is to be aware of all transactions. In the mint-based model, the mint was aware of all transactions and decided which arrived first. To accomplish this without a third trusted party, transactions must be publicly announced. And we need a system for participants to agree on a single history of the order in which they were received. The payee needs proof that at the time of each transaction, the majority of nodes agreed it was the first received. All right, so this is essentially talking about the ledger, right? You need an entire history of transactions. If you the only way to know that something wasn't double spent is to be aware of all the transactions, every transaction that's ever happened, so you can check that it's not being double spent right now to you. And in order to do that, you need the entire ledger. And this is what we now call the blockchain. And this is what you download when you're running a full node. The payee needs proof that at the time of each transaction, the majority of nodes agreed that it was first received. So if I'm receiving a transaction, this is how I verify that it hasn't been double spent yet without a trusted third party. You just download the entire ledger and check against it. And this is what full node software essentially does. All right. timestamp server. The solution we propose begins with a timestamp server. A timestamp server works by taking a hash of the block of items to be timestamped and widely publishing the hash, such as in a newspaper or Usenet post. The timestamp proves that the data must have existed at the time, obviously, in order to get into the hash. Each timestamp includes the previous timestamp in its hash, forming a chain with each additional timestamp reinforcing the ones before it. So this is in the white paper, it's known as a timestamp server. We call it a blockchain now, but basically it's each block that has a timestamp on it. And this is talking about publishing it in a newspaper or a Usenet post. So basically publicly announce it, and this will change with the next session. But that's one way in which you can have a chain of timestamps, is that you use the hash of the previous block, and if you include it in the current block, each page in the ledger sort of has a reference to the previous one, and that's what Satoshi calls the timestamp server. It's it continuously generates this thing. Now you need to do this in a decentralized way. If it's a centralized timestamp server, that's very easy, and there are many services out there that already run something like this. But to do it in a decentralized manner, in a way that you don't have a single point of failure or a single place that you have to trust, you have to do it a little differently. And this is where we get to proof of work. To implement a distributed timestamp server on a peer-to-peer basis, we need to use a proof of work system similar to Adam Back's Hashcash. All right, so Adam Back's Hashcash is basically this idea, well, it'll get described. Rather than newspaper or Usenet post. Like I said, that this changes with proof of work because that's what Satoshi proposes in 3, but says, okay, well, you can't really do it that way because then you're giving control to the newspaper or whoever's running the Usenet. The proof of work involves scanning for a value that, when hashed, such as with SHA-256, the hash begins with a number of 0 bits. So basically, it's saying that the proof of work is taking the SHA-256 of something, of some blob of data, and then when you hash it, it has it leads with a bunch of zeros, and this is like the probability that the very first bit is 0 versus a 1 is 50%, that the first 2 bits are 0 is 25%, first 3 bits 12.5%, and so on. So you can very finely tweak how hard the proof of work is going to be, and that was Adam Back's idea, and that's what we were looking at. That's what Satoshi found. The average work required is exponential in the number of 0 bits required and can be verified by executing a single hash. Yeah, right. So like I said, first bit being 0, 50%, first 2 bits being 0, 25%, and it halves with each bit. So it goes up exponentially very quickly. If you require 10 zeros versus 10 0 bits versus 20 0 bits, the second one is going to be like 1,000 times harder. And not like doubly harder, and so on. So it's exponential. It goes up at an exponential basis. For our timestamp network, we implement proof of work by incrementing a nonce in the block until a value is found that gives the block's hash the required 0 bits. Once the CPU effort has been expended to make it satisfy proof of work, the block cannot be changed without redoing the work. As later blocks are chained after it, the work to change the block would include redoing all the blocks after it. And this is the security behind proof of work. It's essentially that every block has to satisfy proof of work, which is a bunch of leading zeros. But finding that gets exponentially hard with each bit. And depending on the number of computers on the network, you need to do at least that amount of work to reverse a single block. But to reverse something 2 blocks before, you have to reverse both blocks. You have to find 2 proofs of work. To reverse something that's 100 blocks in the past, you have to reverse all 100. You have to find 100 proofs of work. So this gets harder and harder and harder, and that's the security around proof of work that's very cleverly designed here. The proof of work also solves the problem of determining representation in majority decision making. If the majority were based on one IP address, one vote, it could be subverted by anyone able to allocate many IPs. He's describing basically a Sybil attack. Proof of work is essentially one CPU, one vote. The majority decision is represented by the longest chain, which has the greatest proof of work effort invested in it. If a majority of CPU power is controlled by honest nodes, the honest chain will grow fastest and outpace any competing chains. To modify a pass block, an attacker would have to redo the proof of work of the block and all blocks after it, and then catch up with and surpass the work of honest nodes. We will show later that the probability of a slower attacker catching up diminishes exponentially as subsequent blocks are added. This is, again, describing basically the idea that subverting proof of work, especially as you go further and further back in the past, becomes harder and harder and requires more and more CPU power. This is not exactly correct, though. So it's not one CPU, one vote. It's the ability to add hashes and so on. And also the whole idea of this is more machine-based, but there's also something called the social consensus, which is basically if you're running your own node, you're master of your own node. And that's something that I don't think Satoshi quite foresaw in this particular section. To compensate for increasing hardware speed and varying interests in running nodes over time, the proof of work difficulty is determined by moving average targeting a number of blocks per hour. If they're generated too fast, the difficulty increases. And this is almost like a throwaway part of part 4, but this is absolutely critical to how Bitcoin works. There's an automatic difficulty adjustment based on the amount of hashing power that comes on the network. And this is what makes Bitcoin so remarkable, is that it gets more difficult as more people try to mine. And it gets less difficult as less people try to mine. And this is the difficulty adjustment that happens on a regular basis. In Bitcoin, it's every 2 weeks. But that's the really truly remarkable thing about it. Network. The steps to run the network are as follows. New transactions are broadcast to all nodes. Each node collects new transactions into a block. Each node works on finding difficult proof of work for its block. When a node finds proof of work, it broadcasts the block to all nodes. Nodes accept the block only if all transactions in it are valid and not already spent. Nodes express their acceptance of the block by working on creating the next block in the chain using the hash of the accepted block as the previous hash. All right, so let's go through each one. Transactions are broadcast to everybody. Every node collects all the transactions into a block, and then each node works on finding proof of work. So back then, at least at the beginning, every computer was also a miner. So that's why step 3 is there. When a node finds a proof of work, it broadcasts the block to all nodes. So if you successfully mine a block, you broadcast. Nodes accept the block only if the transactions in it are valid and not already spent. So if you see that it's not double spending and it's valid and the proof of work is valid and everything, then you accept it into your ledger. Nodes express their acceptance of the block by working on creating the next block in the chain using the hash of the accepted block as the previous hash. So now everyone works on the next block, and that's how quote unquote it's accepted. Nodes always consider the longest chain to be the correct one and will keep working on extending it. If 2 nodes broadcast different versions of the next block simultaneously, some nodes may receive one or the other first. In that case, they work on the first one they receive but save the other branch in case it becomes longer. The tie will be broken when the next proof of work is found and one branch becomes longer. The nodes that were working on the other branch will then switch to the longer one. So this is the tiebreaker, and this is also absolutely brilliant because figuring out which one to take requires this very thing. If you can figure out, oh, okay, well, that one's better than the other, you need some objective metric, and length of the chain, or currently it's most accumulated proof of work, decides who wins, and that's how you keep it objective. New transaction broadcasts do not necessarily need to reach all nodes. As long as they reach many nodes, they will get into a block before long. Block broadcasts are also tolerant of drop messages. If a node does not receive a block, it will request it when it receives the next block and realizes it missed one. That's what's called an orphan block. So you don't know what the parent block is, so you go around and ask her about it. So that's how the whole network works, and it's extremely resilient because you can just request whatever it is that you're missing. Incentive. By convention, the first transaction in a block is a special transaction that starts a new coin owned by the creator of the block. This adds an incentive for nodes to support the network and provides a way to initially distribute coins into circulation since there is no central authority to issue them. The steady addition of a constant amount of new coins is analogous to gold miners expanding resources to add gold to circulation. In our case, it is CPU time and electricity that is expended. So this is again one of those like really brilliant paragraphs in the whole paper, and it's basically talking about the monetary policy of this whole network, and it is set in stone from the moment that the entire network goes live. And it is that basically the money is created into the network as a result of finding blocks, right? This is what we now call the Coinbase transaction. It's not, the word Coinbase isn't in the paper, but the idea is that the first transaction of every block is entitled to some amount of reward, and that gets into new coins come into circulation. And this analogy with gold miners is absolutely correct, because in a way, every miner is looking for a proof of work. And instead of dirt and rock that you're searching through a bunch of numbers. And that requires CPU time and electricity. The incentive can also be funded with transaction fees. If the output value of a transaction is less than its input value, the difference is a transaction fee that is added to the incentive value of the block containing the transaction. Once a predetermined number of coins have entered circulation, the incentive can transition entirely to transaction fees and be completely inflation-free. Wow, the amount of economics that goes into this particular paragraph. So essentially, miners also take the transaction fees. If the output is less than the input, this gives an incentive to a miner to include a transaction in a block. And once a predetermined number of coins have entered circulation, the incentive can transition entirely to transaction fees and be completely inflation-free. So this happens in 2140, but this was foreseen, right? This is a question that I receive all the time. What happens when miners don't get any Coinbase award? Well, I mean, Satoshi foresaw this from the very beginning. Then once a predetermined number of coins have entered into circulation, the incentive can transition entirely to transaction fees and be completely inflation-free. This is 21 million Bitcoins. Once that's happened, then it can be inflation-free. It's a deflation, or there's no more inflation happening at all. The incentive may help encourage nodes to stay honest. If a greedy attacker is able to assemble more CPU power than all the honest nodes, he would have to choose between using it to defraud people by stealing back his payments or using it to generate new coins. He ought to find it more profitable to play by the rules. Such rules that favor him with more new coins than everyone else combined, than to undermine the system and the validity of his own wealth. And this is a key part of the incentives for Bitcoin, is that if you have a majority of the hashing power, it is far more profitable just to keep mining and making more money that way than to try to go change history and double spend somebody and take money from them. And this is one of the most brilliant sections in the entire paper is all of the incentives that were laid out in just these three paragraphs. It's new coins coming into circulation, a cap on the number of coins that will ever be, and the whole fee market, and preventing sort of 51% attacks. Satoshi foresaw sort of a lot of the incentives that would come into play here. All right, so I'm going to go through 7, 8, 9, 10, 11, and 12 next time. But hopefully that helps you. Let's see if there are any questions. Thanks for the link. Difficulty adjustment. Yeah, the Guinness in this paper is mind-blowing. Market reopened after tripping circuit breaker. Okay, well, all right. Well, so it sounds like there aren't any questions. Anyway, that's basically it for this episode of White Paper Wednesday. Next week, I'll go through 7, 8, 9, and 10, or part 2 of the Satoshi White Paper. In the meantime, here, let me go through some of the stuff that I have available. You can read my book, Programming Bitcoin, It's available on Amazon for $45.66. You can also get the Little Bitcoin book on Amazon. It's available on Kindle, audiobook, paperback. It's available for $11.39. All right, so that's about it, and hopefully that helps you. Yeah, let me know in the comments if you find this useful or if you want more clarity on something or other. Fiat delenda est. This song is done.